Hi.
I can run and get one. Yeah, I can run upstairs and get one.
Finish your action, run up.
Okay.
Now that you're doing that.
Well, you don't have a key in my office. Okay, hi. Well, I'd like to welcome here today Dan Gildea, who's at University of Rochester, actually I think in my old office. He did his undergraduate and master's and PhD all at Berkeley, his PhD under Nelson Morgan, before spending 2 years at Penn doing a postdoc with Martha Palmer, where among other things he was one of the people behind PropBag, together with Martha and Paul Kingsbury. Dan works on all kinds of things syntactic. In particular, grammar induction, getting from syntax to semantic roles, and what he's going to be talking about today, which is using syntax and machine translation, where he is very carefully, probably more carefully than almost anyone, has tried a number of things to see what helps and what doesn't. So,
okay, thank you very much. It's very nice to be here. I'll be talking about syntactic models of alignment. A lot of this is work with my student Hao Zhang at Rochester. So the overall idea for everything in this talk is we want to get some kind of hybrid in machine translation between statistical approaches, which traditionally have been at the word level, and symbolic systems that use more syntax and semantics in analyze, transfer, and generate paradigms. So here's what I'm going to talk about. So the first section of the talk will be sort of empirical results for alignment with a lot of different combinations of models and features. So I'll sort of talk about what the categorization of tree-based models for alignments are. I'll talk about ways to extend them to handle syntactic divergence, talk about representing syntax with dependencies or constituents, talk about an extension to what I call syntactically unsupervised models to let the probabilities be lexicalized. The second part of the talk will be new work that you'll be the first people to hear about. This is sort of more theoretical work on synchronous context free grammars and how you can take a general synchronous context free grammar and reduce the branching factor, and how often and how you can do that. Okay, so this is sort of the general picture for using syntactic trees to do alignment between parallel strings. So,
it's the red button.
Great, thanks. Great. So here's a sequence of operations that you might use to take a Chinese string to an English string. So do reordering at one level in the tree, decide what the individual word pair translations are going to be, and then here we're getting rid of some deleted material, and we end up with the English tree in this case. So you can do this sort of thing in several different ways, and one way to break it down is how do you use a parser, or how do you use a grammar for your two languages. So there's the no parser, what I call the syntactically unsupervised approach. So this is this was Dekai Wu's inversion transduction grammar. It learns trees, but there's no parser that's used as an input to the system. It just comes from parallel text. Or you can parse one of your languages with a statistical parser, and then do projection onto the other language. So that's the tree to string approach that Kenji Yamada and Kevin Knight pioneered. Or you can try to use syntactic information for both languages. So why not try to use a tree for both sides of your corpus and and match the two trees, so the tree-to-tree approach. And I'll actually be talking about all three of these and comparing them. So the inversion transduction grammar, or what I'm calling syntactically unsupervised, it's a parallel grammar that has rules of this basic form. So first of all, everything's binary. So we have a terminal going to two non-terminals, and there's two types of rules. So something is either in the same order in both languages or in reverse order as you go from one language to another. So these are the non-terminal rules, and then this is the generating a terminal, which in this case is actually a pair of one English word and one French word. So if you try to parse with this kind of synchronous grammar in two languages, there's sort of two ways of looking at it. So the grid version and the tree version. So this is just a simple example sentence with three words in French and English, and here we have one rule that's inverted, so see them comes out in reverse order from les voix in French, and then this is in the same order in both languages, and if you sort of draw the grid of which words are aligned to which, the inverted alignment is just a diagonal. In this direction, we're building a constituent that covers this bigger cell, and then we have a diagonal block in the other direction is a straight rule production. Okay, so the picture that I started out with would really be a case of tree-to-string alignment. So if you have here the parser output for English, and you project it onto the Chinese string. Here the operations are doing reordering at different levels of the tree. So you're allowed to, for any node, reorder its children into any of the n factorial possibilities with some probability that's just conditioned on local things in the tree. And then you have word level translations, which are also parameterized by pairs of probabilities for individual words. And you do some insertions and deletions and get back to the English tree that you started with. So if you want to do alignment with a model like this, or do EM to train the parameters, it's also a synchronous parsing problem, and you can also look at it in terms of finding this grid and building bigger and bigger cells from the bottom up. Sorry, you can't see my my trees better somehow. The resolution doesn't seem to be good enough, but the idea is that you're starting with a tree on one side, so in English typically, this is fixed, and as you decide which word pairs to align here, you're building a projected reordered version of that tree in the other language. And since the trees in the parser output that we start with are not necessarily binary, that means that we can get some reorderings that actually aren't allowed with ITG, and this is one example. So none of these boxes are adjacent diagonally, which means you can't combine any two of them with ITG. But with the tree-to-string model, you can get this if it's all under one node in the original tree. But of course, you're still constrained by other features of that tree.
Then, so it's not showing, but
yeah.
It's a tree that takes A and produces A1 through A4, and so it's sort of a sideways tree.
Yeah, it's a sideways tree. This is one branching with 4 children, and then there may be other subtrees under each of these.
I could think of some further details in there. I could think maybe A3, A4 make a constituent which combines with maybe A2 or whatever. I could imagine a tree. And then you're saying that that would correspond to a particular tree on this side, a projected tree.
So if I'm taking this as fixed, and then depending on what I align inside the box, I can get the tree coming out in different orderings down here.
And you're going to respect that alignment to the extent that it lets you build a tree.
Yes. So the alignment is actually just a probabilistic thing. So for in each atomic cell in the grid, you have a word probability, and we're doing dynamic programming to find the best overall alignment and the best projected tree on the bottom. Okay. So the version where you start with parser output in both languages also works by sort of transforming a parser output tree into with a set of operations. But before we just had reordering. That was the only, we had no single level reordering of the tree. And because the tree of the other language probably isn't going to look, have exactly the same form, be exactly isomorphic, now it's probably a good idea to sort of expand things by having a bigger set of operations. So you can merge two nodes that are immediately adjacent in one tree to make one node in the other, or in the opposite directions, split a node into two nodes, or grab two nodes on both sides as a unit. And these are all, however...
I don't understand the last,
okay.
the group business.
Okay, so what this does is it says that a pair on one side is aligned with a pair on the other side. The reason to group the two is that now you can reorder all of their children as a unit, which you wouldn't be able to do unless you grabbed.
Reorder, that means they can be moved also. In other words, something that was sticking out of one of these can now be sticking out of the other.
Yeah, and you don't, it's not just which node it comes under, but just being able to reorder things that, so mix together the what was under one node and the other node.
From a split followed by two splits followed by a merge?
Yeah, you can't follow a split by a merge. You can't follow one of these things with another. So the way this works is first you choose what the grouping is. Choose in each case whether it's going to be 1-to-1, 2-to-1, and so on. Then you do the reordering, and that's it.
This is just about the sizes of elementary trees in a tree pair. So merge is a 2-node tree being paired with a 1-node tree. Or I'm sorry, these are the, if you ignore the substitution nodes.
So this is
TSG.
It stops being binary, right, if you have a merge?
it's already not binary. So
Oh, it's already not.
so yeah, so even with before we had two trees and the tree to string, our parser output is not necessarily binary. And so there we were considering all reordering. So if something has 4 nodes, it can, all 24 reorderings are considered in the alignment.
And the previous model, all that it had was merges.
All that it had was, I didn't even write on here.
Well, but the lack of correspondence that you gave us before was sort of a merge, right? So
this?
Yeah.
Is this what you're looking at? So
that it says to say that A2 and A4 are now a constituent where they weren't before.
This whole thing is a constituent.
In
So-
English.
And in our, this is, actually, I didn't talk about this, but this is just showing, so this is making it binary in the projected tree, which is just a way of speeding up the dynamic programming. So if you, so doing this is computationally hard because there's n factorial reorderings. If you group together subsets of the nodes as you go, it's still exponential, but it's not factorial. So that just makes things faster. But that's not related to the merge or split. Okay. Any other questions about this? Okay, so this is what the operations look like. So grouping these two nodes together, and this will actually, well, we need to do this if there's only one node in the other tree, but it also means that we can get a reordering that wasn't possible in the tree-to-string model. So we can also get this 3 down between the 1 and the 2. And the group also lets you have more, bigger set of reorderings at the leaves of the tree. But I said that you can only grab up to 2 nodes on either side. And that's just to keep the complexity under control and sort of keep a relatively local set of operations on the trees. And that ends up meaning that if you start out with a tree that looks like this, well, you're not allowed to group all 3 of those together, which means you also can't get this particular reordering of all 4 leaves, actually regardless of what the structure above them looks like in the other language.
E and D were
you could only,
let's
okay.
talk about the merge first
Okay.
of all. What is being merged in the merge?
A and B. You can only merge.
They don't have to be on the same level.
No, one has to be a child of the other. So they have to be sort of adjacent in the tree, which actually means that one is a child of the other.
Okay.
And
on one side you have a flat construction, and the other side is a nested construction.
yeah, exactly. Yeah. And so
And in the group?
So in group,
What is legal again in the group?
what is what?
Legal?
So you can grab 2 nodes on both sides. So something that would be legal would be, say I didn't have a node here,
Yeah.
and I group these together.
A and B you would group together.
Yeah, so I group A and B together, and then on the other side, I have something where there's also 2 nodes, but maybe only 4 is under one of the nodes on that side. So everything that's under the pair is kind of mixed around as a unit.
So both merge, group, and everything always deals with pairs of nodes which are sons of each other.
Yes, yeah, exactly. Yeah.
Not sisters.
Yep, exactly. Okay, so here's the complexity for all of these things. So actually this is the same whether you're doing EM to learn the parameters or just finding the best alignment with the Viterbi algorithm. So N is the length of the sentence in either language, and M is the maximum number of children that a node can have in your grammar. And T is the tree, so this is the number of nodes in the tree, which is probably about the same as the number of words in your sentence. So, ITG is n to the 6th. Because we were assuming everything's binary, we just have, it's like chart parsing in one language, n to the 3rd times chart parsing in the other. So we have 3 indices into each of our 2 dimensions. And in tree to string, if we do the grouping of subsets of children of a node that I talked about, that keeps things just n to the 3rd. So we're just combining 2 subconstituents at a time. But we have this term, this m factorial term for all possible reorderings under a node So its m children can be reordered m factorial ways. And you do this for each node in the tree.
Right, so, and there are big O of n such nodes.
Presumably, yeah.
So, okay, yeah, I'm going to hold this question.
Okay. So tree to tree, actually now, since we're not working with the strings at all, we're just working in nodes on both sides. So we're considering all pairs of nodes from the two trees as possible aligned pairs. So that's the t squared. And the reason this is 2m factorial now is that, well, if you group two nodes together, they may have 2m children, and you can do all reorderings. So here the length of the sentence actually doesn't really matter so much anymore, but the branching factor is really important. Okay, so I already mentioned the tree structure can constrain what alignments you get. This is one example that wouldn't be possible with the tree to string, so assume we're not doing any grouping. We can't get this thing down inside these two. And if you look at the three leaves here, and they have 6 possible reorderings, and 2 of them involve moving this inside the other 2, so 2 out of the 6 are impossible. In general, well, we could solve this by grouping 2 nodes together, but of course, if they were farther apart, there's still a lot of alignments that you can't get with the extended operations. And all of the 3 models constrain the alignments, but they do it in different ways. So, for example, with ITG, we couldn't get the 4-way reordering where no 2 things are adjacent in both languages. Tree to string, we can't get this. With tree to tree, we might get this particular example, but we might also have other constraints from the tree on the other side. Okay. So, so a way out of this is to relax the constraint that the 2 trees have to correspond exactly. And so one way to do that is just to add one more operation to the model, which lets you copy a subtree. So I call this cloning. This means that with some probability, when I'm aligning stuff under B, I just decide to insert a clone of something, and it's some other node in the tree, so I also, with some probability, pick this as what gets cloned. And now I can get this ordering where 3 has to come down between 1 and 2. So in order to keep the dynamic programming intact, this doesn't change anything about the version or the original copy of this node. So to get this exact output, you would also have to delete the original copy, but there's nothing in the model that enforces that. It's just something that presumably will happen if you're doing alignment, and there is actually only 1 copy in the string pair that you have. So it's kind of like model 1 for trees. So trees can have any number of copies, and there's no explicit fertility parameter that ties those copies together. Okay, so here's an example of what happens if you apply cloning to treat a string model with a Korean-English sentence pair. So this is, let's see, this is the Korean tree after it's been reordered into the English word order. So the sentence is, how many pairs of gloves is each of you issued? And so what's happened here is I decided to generate a clone here, and then decided to grab that from this particular node. And that was the only way to get this material at the end of the English sentence in the alignment. And everything under the original copy got deleted, but again, that's only because, well, that's the only way to make the alignment work. There's only one copy of it in the English, but again, there's nothing in the model that says that once we've copied this, that this has to go to null. Okay, so in this particular example, it's sort of corresponds to the fact that you have WH movement in English and not in Korean. So how many pairs is at the beginning of the English sentence? But of course, it doesn't know that this is a question or anything like that. Questions on this?
So when you copy are you copying the node or are you copying the whole subtree?
The whole subtree. So once you copy the node, everything under it sort of comes with it. And once you make a copy, the operations that happen below it are not linked to the original copy. So for example, I reordered this here, but not over there. Yeah?
Is there a reason you did it this way rather than copying the WH phrase to the front?
This is what came out of my system, so I don't really know why, but
But from the perspective of the model, that would have been a sort of possible analysis as well.
yeah. So you could
you would have had to copy the whole VP because gloves isn't under. You have to copy the whole VP, then delete the VP for how many pairs?
Right. Which suggests that the Korean tree is a little bit loony. Right. That it's sort of a bad parse of the Korean sentence.
Although it was done by hand. I assume this is the hand Korean parse.
Yeah, so it has to, the syntactic structure is just not the same in Korean. It's not parallel. So I guess the only way to get this at the end and get this stuff and this thing at the beginning was to do it this way.
No, but might you say it's loony because the way it appears to me, it looks like they're saying the sentence is something like, let's see, issued in gloves. Those are the main things. That's what I tied at the top there in Korean. And then each of you and how many pairs are the other arguments of issued.
Right, so issued has 3 arguments. You, gloves.
Right, and they don't correspond to where we put those arguments in English.
It's funny to think of issued as a 3+ predicate.
It looks like
Yeah, I don't know.
a topic. It looks like a topic.
Yeah.
College. How many should you do?
Right.
Oh,
Well, this, yeah. I actually don't know what the Korean word order is here. So.
Sorry, question about the example.
Yeah.
So maybe it's worth asking about the discrepancy between being able to clone entire subtrees, but apparently not being able to delete entire subtrees. I think I understand the reason for that, but you've deleted the 3 words at the left individually.
Yeah, so there is actually in my implementation of the tree-to-tree, you can delete an entire subtree. So once you decide to delete a particular node, everything under it is constrained to disappear.
Why is
Here,
that cheaper than this?
well, here I guess it doesn't really seem like there's a benefit to doing that. So if there's nothing matching any of these things at the bottom, we don't really care what this internal structure looks like in the tree-to-string. So there's not really much of a difference between deleting at the bottom and deleting at the top. So.
Well, that depends on whether there's a cost for deletion.
Well, there is a cost for deletion, and there might be some benefit to sort of tying things together, but it isn't sort of as immediately apparent in the tree-to-string. So. Okay, so this is just an overview of what all the parameters to these models are that we're learning with EM in both cases. So there's the individual word level translation probabilities that are actually independent of everything else. And there's the reordering probability, which is conditioned on the context-free grammar rules of the parent and its children. And if you add cloning, there's actually two parameters to this. So there's deciding to insert a clone under a node and then choosing which node it gets copied from. So in the tree-to-tree version, you have basically the same set of parameters, but there's this new step where you do the grouping and splitting. And so this is a probability that has, it actually chooses, for each node, it chooses either not to group anything to keep it as a singleton, or it chooses one of the children to be grouped together with the parent. And that's conditioned on, again, on the grammar rule of the parent and its children.
On which grammar rule? The one that will be affected?
This happens on both sides. So,
Oh, actually, yeah.
so there's one of these on both sides.
But one of them is effective. Oh.
I'm sorry?
The merge may occur only on one side.
Well, otherwise we're calling it splitting, but that's kind of like merging going in the other direction. So, so merging, in merging you choose on side A, I'm grouping child number 2 with the parent. In splitting, you that's just saying now on language B, I'm generating this new child under the parent. Just kind of like grouping it. So it's analogous.
And once I carry out something like a merge, then now different nodes, do nodes keep corresponding?
So once
they used to correspond.
Once you merge,
I can't see the geometry. That's
okay. Once you've merged, if you do a merge, then those two nodes lose their individual identity, and
so therefore you can't operate on them anymore.
Right, but their children correspond collectively to the children on the other side.
Well, their children correspond individually to the children on the other side.
Yeah. Well, yeah.
I mean,
there's a one-to-one mapping.
There's a one-to-one
yeah.
mapping between the set and the other side.
And it almost feels as if there is a synchronous thing going on, that when merge basically says produce one here and a pair there.
Right.
And or it should produce one here and a pair there.
Right.
In our terminology,
I'm calling that
going from here to
split.
there,
Yeah.
it's a split,
Exactly.
but
Exactly.
Otherwise, if you think of it synchronously,
Yeah. It's symmetric. Yeah.
This make clone. So if I know where I'm going to clone, is epsilon in any way conditioned on, for example, I might want to say I want to clone either like immediate uncles and aunts, or it could be any.
It could. So I didn't do what you're describing, although you could implement that without breaking the dynamic programming.
Right, I'm thinking it
So
might constrain it, and that might be all the cloning you need. I
Yeah.
don't know what kind of cloning.
So this is
Yeah.
just the probability of taking some subtrees and adding it anywhere in the tree?
Yes. So this is that you decide you're going to add something, and this is where you make the copy from.
Okay.
Okay. And this could be conditioned on more information, but I'm saying there's just one of these for NPs and one for VPs and so on.
And so it is conditioned a little bit on where you're cloning.
Yeah,
It might be
very little bit, yeah.
There's no attention to C command, for example, which you might think would be useful.
And the deletion, I see how you might do that with the lexical translation, but the deletion of a subtree?
Okay, so deletion of subtrees doesn't happen over here. You just delete at the leaves. Here, you can actually both delete and insert internal nodes in the tree. So that's why I'm calling this p-align instead of p-order. So the difference between aligning and ordering is that you can insert and delete. So if you delete, or I guess maybe it's easier to think of it as, to keep things symmetric, as deleting on either side. Once you've deleted, everything underneath doesn't correspond to the other tree. So everything is also deleted down the subtree. So this alpha is actually a string of symbols that some of them are numbers that are the permutations, the reordering, and some of them say insert a node here, delete a node here.
So I could think of it this way. I could think of a node producing children, and I could always add this special child, which is the null child.
Mm-hmm.
So that on this side, if any node gets aligned to the null child, it's like saying it's going to be deleted.
Yeah, although you can align more than one thing to the null child, whereas otherwise it's a one-to-one mapping. Yeah. Okay. So I ran all of these things trained on parallel text and evaluated by how well they correspond to human word level alignments. And so the metric is alignment error rate, which is measuring the overlap of how well your system's alignments agree with the gold standard alignments. And this is broken down to have possible alignments and sure alignments in your gold standard, where basically the possibles you can get credit either way. Although I think I'm only going to tell you about Chinese results, which only have one type of gold standard alignment. So the training data was relatively small amount of parallel Chinese-English text, 18,000 sentences, limited to 25 words long on either side, and the test data was 47 hand-aligned sentences from Rebecca Hua, and there was another set that was used for cross-validation and basically developing the models.
And align like string to string.
I'm sorry?
And align, I mean.
They're word to word, so they're. I mean,
Word to word, that's what I meant.
Yeah, and so there's no trees.
Completely, yes, exactly.
There's no trees, and in fact, the hand alignments also can have many to one alignments in either direction. So you can have one Chinese word going to many English or vice versa, and none of these models will do that unless you clone.
And, I mean, this is, 47 sounds like a small number of sentences.
I agree.
Might around more? Or?
That's all I had. I agree.
What is it? Well, I mean, I don't mean it, but what has she been doing since 2002?
Well, yeah. I'm probably the one who should be doing it since I'm using the data now. But. Okay, so this is what we got out in terms of alignment error rate. So actually the best here is the inversion transduction grammar. It's doing better than IBM Model 4, which is word level, no trees. And here the tree to string is doing a little bit better than the tree to tree. And the cloning is helping. So the comparing the tree to string without cloning and tree to string with cloning is giving us 2 points. Okay. So here's an example of a tree, what a tree to tree model has to do. So a Chinese tree and an English tree. The sentence is 14 Chinese open border cities make significant achievements in economic construction. And if you look at this noun phrase, it actually does correspond to this noun phrase in Chinese, but the internal structure is different, as you can see. So there's kind of a whole nother level in here. Some of this has to do with just differences in annotation style between the Chinese and English tree bank, so the English is flatter, especially for NPs. And then one other difference is that there's this measure word in Chinese, which obviously also has some internal tree nodes on top of it that don't exist in English. So we thought that these two things might look more similar in a dependency representation. So this is taking the two trees from the last slide, using headword rules to propagate headwords up the trees, and flattening things out so that you just have head modifier relations with heads inside the tree now. Now these two noun phrases basically look the same except for this, and we still have the measure word in Chinese. So,
But there's a big difference between the root of the Chinese tree
yeah.
and the root of the English.
Yeah, so the main verb here is actually an adjective, and this thing is a couple levels down here, and let's see. Yeah, so this is at the lowest level in English, but it's the top in Chinese. Okay, so I tried running the tree-to-tree model on the dependency version of the trees, and it's basically the same model with one extra operation, which is that if you group two to two, so if you group two nodes together on both sides, because it matters how they align internally, now that there's words inside these things, you can swap the heads, so you can have the A go down to the bottom and the B go up to the top. So here, first you choose the grouping on both sides, then there's this one extra operation that says that you swap, and that's just one number that's not conditioned on anything, and then you translate both words and do the reordering of the children. Okay, so it turned out that this did not help. So the alignment error rate is higher with the dependency version than the constituent version. And well, it's the same tree, so it has to do with, again, the fact that, well, the thing that's at the top here is several levels down, even though it's sort of what it's adjacent to is aligned in both cases. Now that you have to sort of get the level in the tree correct, that also can create more ways to go wrong. And I did some analysis of the trees to figure out how often this was happening. So using the the gold standard alignments, you can look for pairs of constituents on both sides that are consistently aligned. So everything under here points to something that's under here, and vice versa if you follow the arrows backwards. And you can also look at what the headword rules are doing. So once we've picked these two pairs, or these two constituents as being consistent, turns out that if you follow down the headword rules, you get a headword on both sides that is also aligned. So cities is cities. And I just calculated, okay, first of all, for all English constituents in the trees, how many of them have some Chinese constituent that is consistently aligned? So everything under one subtree points to something under the other subtree, and vice versa. So regardless of what you have to do to align the rest of the tree.
This is on your 47 sentences?
Yes, yes. So this is using gold standard alignments. And so this is 40%. How many of those agree in terms of the headword? 67%. So the remaining 1/3 are going to be cases where it's actually more difficult to do the alignment in the treated, or I'm sorry, in the dependency representation, because what's at the top level is different in the two trees. I also tried doing this with Chinese trees from the Chinese tree bank rather than automatic parser output. I didn't have gold standard trees on both sides, but just to see how much of this might be due to parser error. And actually the proportion of consistently aligned constituents is a little bit better, but the alignment error rate actually goes up, so it doesn't look like parser error is the problem.
Is the fact that if, like, let's say that the Chinese and English constituent aligned, but their heads are not aligned to each other within that, is that because we have sort of the wrong head percolation rules maybe in the different sets for Chinese, or is this just that when people do translations?
It's more the latter. So yeah, it just, if you look at the two sentences, there's just not a direct syntactic correspondence. So what's the verb in English is not the verb in Chinese, but like in this example. So.
And this is not dominated by a few lexical constructions or something? It's possible that...
I don't think so. Okay, so that's it for the tree-to-tree business. I want to talk about one other alignment model, which is a lexicalized version of ITG, where okay, we go back to assuming everything's binary. We say that the trees are just going to come out from the data. We're not using a parser, but we have headword percolation rules here, and we can condition the reordering probabilities on what the head at each level is. So the grammar looks like this now. So instead of just having straight rules and inverted rules, now we have 4 different types, because you also have to decide, is the lexicalization English and French word getting passed down to the first child or the second child? And then there's a new type of rule that picks the lexicalization for the non-head child. So this guy, for example, when you actually generate the words at the leaves of the tree, you've already decided what they are. So this rule isn't really doing anything. Has probability 1. But what this means now is that we can decide whether to invert or not condition on these head words. Okay, so we trained this using EM, and it's more computationally complex. So with the Headword choice, it's now n to the 8 instead of n to the 6, because there's an extra index for choosing the head. So this is on sentences just up to length 15 on either side, which is the most that we could do full EM on. And now the error rate is higher because we have smaller amount of data, but we're getting a win from the lexicalization. Okay, actually that's it for this section. So any questions before I move into the theory part?
Now, I'm still quite puzzled by the fact that you have this large fraction where the heads of constituents are not word aligned, which makes me wonder whether how good these translations are.
Well, how good the parsers are, and how good the heading rules are, and how good
No, I
the constitutional language.
I believe you have manual. Are these based on these? You said you had a tree bank number, so I assume.
So that's for Chinese
Parsers
gold
with
standard
manual.
trees, yeah.
But the head percolation is not manual.
Yeah, but actually my feeling is that that's not really the problem.
Yeah, sure.
Yeah. So the translations are just not that literal, and yeah.
So that's not, I mean, do prepositions come into play there? A preposition says a preposition, right?
They are, and I did a little bit of sort of modifications to the headword rules to see what would happen. And for example, changing the headword of a verb phrase to be the main verb instead of the auxiliary, which actually helped a little bit. So that increased the numbers by about 1 point over what I showed here, but it's still a big gap.
If you wanted to reverse engineer the head percolation rules to get maximal word alignment, then would they look crazy? Or, because,
I think it's, no, actually.
Josh just said if you had a prepositional phrase which was some preposition of an NP and you just make the head of the NP there.
I don't think that's crazy.
No, that would be crazy. And then the question is that, for example, if with a few fixes like that, if the numbers look much better, then it would mean that these are good translations.
It's not. It's only going to increase things a little bit. Is my feeling based on what I've tried.
So I'm just wondering what the take-home lesson of this section is. I can think of a number of things. Two specifically. One is that if these things really aren't very literal translations, then this is a task that's just, you're throwing the wrong machinery at the task. It's just a difficult task that this kind of model is not designed to solve. That's one kind of possible problem. The other possible analysis situation is that, it seems like the take-home lesson of the experiments that you did is pretty depressing, right? Namely that the more brain dead the model, leaving aside IBM Model 4, the more brain dead the model, the better it does. So which suggests actually that the problem isn't necessarily the sophistication of the model, but rather the divergence between the two kinds of parses. That people are saying, well, are they good parses? They might be perfectly good parses, but
that's not what you need for MT.
The people had when they created the English parse and the desiderata they had when they created the Chinese parse were just different. So they represent different sorts of information, so they don't align, and so they're... So why should you expect that we would necessarily be able to map as
Yeah, so I think that basically the trees that you would need to do MT don't necessarily look like the trees that you would draw just looking at one language. So I actually don't think that it's even so much that the grammar formalism that they used designing the tree bank had different desiderata, but they weren't looking at Chinese when they designed it. If you do ITG, it is producing trees, but they're obviously different since the results that we're getting out are different. And I think that the trees that you need to go from Chinese to English are going to look different than from German to English and so on. So I guess that's what I would say the take-home message is.
Well, I don't know which language you know, but it seems to me that it's actually, I know we're under the gun of all sorts of government organizations, but otherwise it seems to me that such research makes only sense if you're dealing with two languages that you know. And you are forcing yourself to do it in Chinese, which you have no idea about. And so you don't know actually how to answer Bob's question, because you don't know what's wrong with the Chinese.
That's true.
I think you're called
that's
for
true.
speak Chinese.
Yeah, that's true.
Yeah, but it should be all lodged in one person.
I'm studying.
It's okay if it's in two different halves of the brain.
Yeah.
No, you're right. We should probably...
if you're going to do avant-garde research on tree alignment, you should do it on an easy task.
Yeah, well,
you still are going to have the trouble that Bob points out, namely that the translations are not going to be literal translations.
We did,
and therefore there will be quirks.
We did this for French, and so I have more of a clue about French, but I guess basically the results were that all of the alignment scores were better, and there's less difference between the modes.
All the alignments
are better.
Are better, yes.
It's much easier, and so.
But these trends are still true.
I'm sorry?
But these trends are still true, even though all of them, all numbers get closer to 100 or 0. But.
Actually, Actually, no. So
Okay, that would be good.
Sorry, when you did English and French, you said the numbers are better, but
all of the alignment error rates are in the 15 range instead of the 40 range.
okay, but does having a clever, doing tree-to-tree alignment, does that start?
I haven't done.
Increment over ITG, say?
I haven't done tree-to-tree alignment for French because I don't have a French parser, but basically the ITG and the tree-to-string are the same. So.
I just wanted to make a point, though, that we're talking about alignment here, and what is a good model for alignment is absolutely not guaranteed to do well for translation and vice versa. Because for alignment, if you have you made the comment about brain-dead models. Say you have a very sophisticated model that restricts the allowable alignments, then you just miss things. Although that kind of constraint might be very good to generate. Mutual information is great to align words, but it's not capable of translation. So, I mean, you can't extrapolate to translation.
Right. So, hopefully, if in an ideal world, if we did translation with this, we might get translations out that were much more literal than what we had in the training data, and maybe that would be okay, but I don't know. Yeah.
A very quick point that you have another part to your talk, right?
Yeah, and I think I'm already out of time, so.
The measurement of correspondence between the trees across languages, it might be interesting to see the same measure of correspondence between trees for English. I've missed the word. A set of paraphrases. I'm not convinced that a set of paraphrases of the same concept in English would have such a high correspondence between trees either. So it would be
Yeah, that's a good point. Yeah. Okay. So should I continue?
You have a choice. You want to give us a quick preview, maybe an abstract version of the second, because I know this was a new part that you.
The abstract.
Let's do 10 minutes. How's that?
Oh, it'll only take 10 minutes. Okay. Okay, so actually all of these models that I've talked about come under the general heading of synchronous context free grammars, and this is kind of just how to write one. So a context free grammar where there's two right-hand sides, one for each language, and we have these subscripts that tell us what the alignment between what the correspondence between the two sets of non-terminals are. And this is kind of the generalized form. So if each X subscript can be any grammar symbol, and they're numbered 1 through n on one side, and then we have this pi, which tells us what the permutation is, what the reordering is. And these can be arbitrarily long, so n symbols on the right-hand side. And so what I'm going to talk about is how to take one of these and reduce the branching factor. So, for example, taking a rule with 4 children in both languages and turning it into 3 rules with that are only binary. So you can do this some of the time, but not all of the time, depending on what the permutation is. So here, this is basically the same thing as ITG parsing, because this is the permutation for this rule, and this is the grouping for this first new rule, and the new second subrule, and this top level rule builds the whole thing. So you're basically parsing, in a way, the rule itself to get a series of smaller rules. And we couldn't do this in ITG, so we still can't turn it into a binary grammar now. And as n increases, as you get more children, there's always more permutations that look like this that you can't reduce to anything smaller. So what I'm going to try to do is figure out when you can make these reductions and when you can't, and do it efficiently. So the sort of the basic data structure is a permutation tree, which is, so each node in this tree is going to end up being a smaller rule in the new factored grammar. And so this is a big 7-way permutation where we grouped 4 of these together, and then this corresponds to this box, which inside it has 2 ITG rules.
So then what you're saying is that if I had a monolingual tree, I could always binarize it once it's synced to bilingual.
Right. So there's
things
no
that are in the binarization can sometimes be
non-adjacent.
yeah.
So there's no Chomsky normal form for synchronous context free grammars.
And you'll have to deal with the biggest size that is irreducible.
Yes,
And
exactly.
that will be the
Yeah.
biggest thing.
Exactly. Okay, so to do this, we want to find this permutation tree, but we want to have a unique version of it. So the idea is to normalize the permutation trees by applying 2 operations to them. So first of all, always use the smallest branching possible. So going back here, we only use something that has 4 children when there's no way to break it down further. And there's also a complication. Even if you only have binary nodes, well, you can either group these 2 first and then all 3, or these 2 first and then all 3. So just to pick a standard way of doing that, we say that if you have a series of binary nodes and they have the same order, that either they're all straight or all inverted, it has to be left branching. So if we have something that looks like this, we can rotate all of the children around to make it right branching. I'm sorry, left branching. So that gives us a unique permutation tree. So the way to take a grammar and figure out whether you can factor it or not is basically a form of shift-reduce parsing. So you look at the grammar rule just as a permutation, so as a series of numbers, and you shift the numbers one at a time, and then you reduce items on the top of your stack whenever you have something that forms a contiguous block. So whenever you have something that you can reduce, and you always do it with the smallest reduction possible. And you just repeat this process. So I'll try to show you why it works, but in terms of the complexity, if you start out with a grammar rule with n children, so you shift n items on to the stack and shift reduce parsing. If you want to reduce it to a branching factor of k, then you might have to look k steps down in the stack to see whether you can reduce something or not. So if you give me an n-ary grammar and tell me you want it to be k-ary, that takes O of nk time. And if you just want to find the best k without specifying what it is beforehand, you may have to go all the way to the bottom of the stack at each time, so it's n squared. Okay. So for the tree that I started with, if you apply this algorithm, you just shift things one at a time, and you can't reduce because there's a gap in the sequence. So there's no 6. There's still no 6. So it's not until we get 4 things that we can group these together, and then we keep shifting and group these 2 because it's the earliest opportunity we have to shift, and then group all of these 3 together till we get basically a parse of the whole rule. And to show why this works, well, basically it's a greedy algorithm, so it always reduces as soon as it can. So if you say that there was some better analysis that ended up factoring things into a lower k, and it's not what the algorithm returned, then there must be some step in this process where we did something that was different from the derivation of the better tree. And so if this R prime is the reduction that we should have made, and actually we're reducing what's in the brackets instead, basically there's just a case analysis of different ways that this can happen. So if this boundary is to the left of where we're reducing now, that's impossible because we would have reduced this as soon as we saw it because it's a greedy algorithm. And if this extends past what we're reducing on both sides, then that's also impossible because it doesn't correspond to the normal form of the permutation tree. So we can never have one rule that's entirely contained within another rule. So what if we reduce something greedily that later we regret doing because we wanted to reduce something that contains part of this? So it's sort of overlapping on both sides. Well, that's also impossible because it would mean that we have to have something that's not a permutation. So, so here's an example where if we're reducing, let's say, this block, what's inside both of those reductions, it must have a hole in it that needs to be plugged. So otherwise we would have reduced this itself as a unit. So here if we're reducing this, sorry you can't see the lines, if this this is what's inside both sets of brackets, and there's a hole that's being filled by this guy. If you reduce with the square brackets, if you take R prime, then it has to also be filled by that block, which means it has to come in from this side, but then this isn't a permutation because we have two dots in the same row. So there's actually several other cases, but if you sort of work through it, you always get the right minimal k with this algorithm. So this is guaranteed to find the synchronous context free grammar with the lowest branching factor. That doesn't necessarily mean that you find the best parsing strategy for a given permutation. So this is an example of a permutation where if you have these sort of three stripes where nothing's immediately adjacent in both dimensions, and imagine extending this out, so growing the size of this whole thing, but keeping this pattern. You can't reduce it at all. So as big as n gets, you can never reduce it into a smaller synchronous context free grammar. But you can find an efficient parsing strategy if you do dynamic programming with chart items that cover two spans in both dimensions. So this just doesn't fit in the synchronous context free grammar formalism because we can't have a symbol that covers two discontinuous things. But if you were to do this, you could parse this particular thing in time n to the 10th if you sort of count up all the indices here, regardless of how big the permutation is. Yeah?
So that's an interesting point. Even within the space of ordinary CFG parsers, you're not guaranteed, I think, to do as well as you can with your algorithm because minimizing the branching factor may be at the expense of sharing less across different rules. And so the grammar constant may end up being worse. Is that correct? In other words, what you've shown is how to binarize, how to k-arize individual rules. But if you want to k-arize the entire grammar at once, you might want to get sharing of some of the new non-terminals that you've introduced across multiple rules, and that might make a difference. So there's also a question about, once you start taking that into account, there's now also questions about the sparsity pattern of the grammar. So under what conditions are certain computations in the, or certain lookups of grammar rules deterministic? there's given x, there's only one y it can combine with, or given that x is going to make z, there's only one y can make that, or given that x and y are going together, there's only one z they can make.
Yeah, so all of this is just looking at one rule at a time. So, and here, it is possible to share some of these new non-terminals, but it's only going to happen by accident. So, okay. So, another interesting question is how many of n factorial permutations can you KRIze for a given k? And so this is a formula for this, and the way it's derived is by taking the permutation trees, actually binarizing them, just to get things into a convenient form. This breaks it down into a bunch of smaller subtrees so we can arrange different numbers of nodes at each of these as long as they all add up to n. But now there's some number of labels that we can assign to these nodes along the spine that tell you which permutations you're using. And so that's what this A is supposed to be. And then this is convolving all ways of dividing up the remaining n-1 nodes among subtrees. And we came up with a more efficient way of calculating this. So basically getting A out of that formula so that instead of, we still have a bunch of convolutions of S, but there's only K of them instead of N. So this is something that you can now evaluate in O of n time for each number. If you want to compute this series, so how many permutations can I forerize as a series as n increases, computing the first n terms as n squared k. And this h is the number of new permutations at each step that can't be reduced into anything smaller. So that's the same as saying it's k factorial times how many things you can k-1-ize for k. Okay, so this is how that series grows for different k's. So this is binary. This is the same as ITG. 3 is the same as 2. Then once you get to 4, it starts getting more interesting. And this is the ratio between successive terms in the sequence. So this is something where we've actually computed these numbers out to several thousand and just watched these ratios converge.
Right, this is as n goes to infinity?
Yeah, so fixing k as n increases the ratio between successive terms. And it turns out that the number of new permutations that you can't reduce at all is a constant fraction of n factorial. So, so there's always lots of new things that you can't reduce, and there's always sort of a growing number of sort of stripes of things that you can reduce to k. And so putting those two facts together, it's easy to show that the things that you can KRIze has to grow strictly less than n factorial, which isn't quite the same thing as proving that the ratio converges to a constant, but it does converge to a constant when we actually compute it. That's it. So, just summarize overall. So ITG was getting the best results for our alignment experiments. The constituents were doing better than the dependencies, and I can tell you how to minimize k in n squared time. The ratio of, as n increases, the fraction of things that you can reduce to k-ary always approaches 0 for any k, because it's growing more slowly than n factorial. But there's also always this big constant ratio of things that you can at least reduce some. So that's it. Thanks.
Or did we ask them all during the talk?
Questions and then a short answer.